Okay, so this standard starts us off with talking about antiderivatives and integration. So we've worked a lot with derivatives, finding rates of change, finding the speed of things. And we've only done a little bit in this realm when we did the trapezoidal rule and when we counted boxes. That was estimating integration, but remember that integration answers the questions how much um, or how far if you're talking about distance. So we'll start with just reading through some of this, but know that we're getting into the other branch of calculus now, but it is closely related to what we've already done, so some of it will look very familiar. We've learned that an antiderivative is a function whose derivative is given. We will learn very soon that the antiderivative gives us a way to calculate exact definite integrals. Okay, so before when we were estimating, now we're going to actually be able to find the exact area underneath the curve, or the exact value of an integral. For this reason, an antiderivative is also called an indefinite integral. Okay, so kind of keep that in mind. The word indefinite is used because there's always a c value that's not determined until you have an initial condition. So we've seen that before. We didn't work this when I gave you an acceleration function and you had to back it up to the position function. We've done that part before. Okay. We have worked consistently now with finding derivatives of functions. One of the notations that we use for derivatives is dy over dx. Consider the following statement. If given dy over dx, find y. Okay, so what is this asking you to do? Well, this is asking you, or telling you, that you are given a rate of change and it wants you to find the original function. Okay? Or you're given the derivative and you're supposed to find the original y. Alright, so consider the statement. If dy equals x fifth dx, find y. Well, you'll notice that the dx is now grouped with the x terms. And you'll note once we get into some of the notation for indefinite integrals and actually integrating functions to find the original, it's written like this. So instead of having dy over dx all the way on the left, you group it with the x terms. This is asking you to do the same thing. Find the original function. Okay. This sets us up to talk about the notation used to find the antiderivative. The integral sign used for this operation is a stretched out f that you'll see later comes from the word sum, or sum up. To indicate that you want to find the indefinite integral of x to the fifth, you would write it like this. Okay, y, or your original function, is going to be the antiderivative of x to the fifth. Dx indicates that this is the derivative with respect to x. And so when we find my original y, which we can do this because you would add an exponent and divide by it, so it would be 1/6 x to the sixth. You don't write the dx again because now this is my original function. It's no longer my derivative. Okay, so the dx is always there to indicate this is the derivative. So maybe that's good. Add in here derivative function. And when you actually find the original function, you no longer need the dx. You do, however, need a plus c because we don't know if there was a constant there to begin with. Okay? So definition of an indefinite integral. Okay, it is a function. That's why it's called indefinite, because depending on your value for c, you could have lots of different things. So your indefinite integral is a function, and it's based off of this expression. So you're integrating a derivative function with respect to x. Okay, so this is true if the derivative is x. Okay, so this is saying basically that this function here, after your sum sign or after your integration sign, is supposed to be what, if you had the original function, what the derivative of it would be. Okay, so again, this is the derivative. All right, in words, an infinite integral of fx dx is a function whose derivative is f of x. Again, making that connection that this function here in the integral is the derivative. And so when you solve this integration problem, you get the original. Okay, the nice thing about finding antiderivatives is you can always check your answers. That's why we do derivatives first, is because when we get to antiderivatives, you can always double check. So like up here, if I find the derivative of 1/6 x to the fifth, I should get what I have in this other expression, which I do. So I know I did it right. The key thing to remember is there is a relationship between the differential dx, can be any variable, at the end of the integral and the argument of the function in the integrand. Okay, so that's kind of wordy, basically meaning these variables have to match up. This can't be f of y dx, and this can't be f of x dy. These variables have to match up in order to continue, which most time they do, but we will get to problems where we have to group x's with x's and y's with y's, and so you do have to keep them separate when you're integrating. All right, go on to the page. Let's run through some basic integration rules here. Okay. So first one we're going to look at is the integral of a constant times a function. All right. So what this would look like is you have integral sign and you have some constant, just a number in front of function. So maybe this is like 1/3 x a fourth or something. Okay, you do need the differential dx there. This is a rule that you can, and actually it's helpful. If you have a constant in front of one function, you can pull it out in front. Okay, so you don't have to deal with it inside here when you're trying to take the antiderivative of this expression. You can just kind of leave it out front and then include it in your final answer. Okay, so basically you can pull constants out. Okay, so these are, again, general rules that are helpful when we're actually setting up problems to find integrals. Okay, the integral of a sum of two functions would basically be this expression. So you have f of x and you have an addition sign or subtraction sign. And it could be 2, it could be 3, but basically you're split up between addition and subtraction signs. You can leave it as such, but the basic idea here is that when you integrate each of them separately. Okay, so we would integrate this function, the original one for that, and then we would integrate this function, and then add those results together. All right, and the integral of a power function looks like this. We have u to the n, and we're going to say du in this case. Now there is a reason why I'm using u here and not, what was I going to say? I'm using u here and not x, okay? Because in this case it could be a lot of different things. But notice that your power here is n, which is going to be an actual number. If you want to integrate, we have to do the opposite of taking the derivative. So instead of subtracting 1 from the exponent, instead of multiplying by the exponent and then subtracting 1, we're going to add 1 to the exponent and then divide. Okay, so in terms here, you'd add 1 to the exponent and then divide by it, and you have u to the n plus 1. You have to plus d. So again, when you actually do this integration rule, the du drops off because you don't need it anymore, because this is no longer the derivative. This is the original. This was the derivative. Okay, we're going to actually apply some of these rules here with some fairly simple functions. Okay, so make an a, b, and a c. All right. We're going to start again with the easy ones and then work our way up, okay? So I want you to integrate 7x to the negative 20 dx. Okay, so we're finding the original function. I have a constant, so actually before I integrate, I'm going to pull the constant out. Again, not essential. You can usually do the problems without doing that. It just makes it nice because then you just have to deal with the the x to the negative 20. All right. Now this is the power rule, or the integral of a power function, because you have a number as your exponent, not a function of x. Okay. So when I integrate this, I'm going to add 1 to the exponent and divide by it. Okay. And this 7 just kind of gets stuck in that expression. So add 1 to the exponent would give me negative 19, divide by it. So 7 over negative 19. And then x to the n plus 1. So again, x to the negative 19th. And then do plus c. And this is indefinite, because at this point I wouldn't be able to plug in x and get a number because I have the c. So until I have more information, I can't get an actual number. But like when we are doing derivatives and you get a derivative function and it gives you the rate of change at any point, this would give you the area underneath the curve at any point. So keep that in mind. All right, next function here that we're going to look at is the integral of x to the 10th plus 2x to the 14th. Okay, so this follows this expression up here, the second one where you're adding two functions together. Now, if you want, you can break it up into the x to the 10th, the x plus, and then I'm going to pull that constant out of 2. But you don't have to. We could integrate it straight from here, and that would be fine. Either way you do it, though. Both of these are going to be, sorry, I should say these ones. Both of these are going to be power functions because you have a number as your exponent. So I'm going to add 1 to the exponent and divide. Add 1 to the exponent here gives me 11, and then I'm going to divide by 11. Adding 1 to the exponent here gives me 15, and then I'm going to divide by 15. And then plus c. Keep in mind that you can always double check it. So if I took the derivative of this function, I should end up with the same thing that I started with right here. So you can always check your work. Okay, last one kind of to start us off here. We have 3x to the negative 2 minus 4x cubed dx. Okay? So again, if you want to split it up, you can, pulling constants out as you go. But you don't have to. We could do it from here. Okay? So I'm going to add 1 to the exponent because, again, these are both power functions because your exponents are numbers. Add 1 to the exponent, you get negative 1, divide by it. So we have negative 3 x to the negative 1 minus, add 1 to the exponent, divide by it. So 4 divided by 4 is 1 plus c. And again, if you're not sure you did that right, you can always take the derivative and check that way. All right, so go ahead and flip. Integration of natural exponential, natural log, and trig functions. Okay, now these ones are pretty essential, especially this natural log one tends to pop up a lot, and power rule one on the other side. So for more complex functions, meaning something that doesn't use the power rule, a method called use substitution is used. We kind of touched on that when we started derivative stuff because I knew this was coming, but now we're going to actually apply it on a greater scale than we did before. Okay, so the integral of the natural exponential. This is saying if you have e to the u du. Okay, so if this is your expression, notice that this is what the derivative rule is when you take the derivative of e to the u. Okay, so if we want to back up a step, if we want to integrate the derivative rule, then you get what we started with, e to the u plus c. Again, if we took the derivative of this, you would get what you started with. So same idea here. The derivative rule for the natural log function is u prime over u, or we should write du over u, or u prime over u. So to get that as my derivative, then my original function would have had to be ln, and we'll explain this a little bit more, but these are usually absolute values around your argument just because you can't have a log of a negative number in general. So plus c. And the integrals of functions. Okay, so again, after every integral symbol here, this in this spot here would have to be the derivative rule for, let's say, sine or cosine. So if we think of, let's say, sine, if we had sine u du, in order to get that as a derivative, my original function would have had to be negative cosine u. Now, again, when I take the derivative of cosine, it's negative sine of u times derivative of u if we have an argument that's more than just x, okay? That's the reason we have to include the negative there because, again, the derivative of cosine is negative sine, so that if we have a negative there, it's going to cancel it out. All right, and then we have the integral rule for cosine of u, which is going to be sine of u, because the derivative of sine is cosine. All right, we have some more. Actually, let's stick one in here. Let's go with secant squared u du. Now, the reason I have to choose that one, and I don't just choose tangent, is because this is the derivative rule for tangent. Just keep that in mind. All right, and then if we go to cosecant, the derivative rule of cosecant is cosecant u, cotangent u du. And so if I get that as my derivative, I would have had to have negative cosecant u plus c. For cotangent, we'll say the derivative of cotangent is cosecant squared of u. And again, we have to include that negative because it's actually negative cosecant squared of u. And the last one, derivative rule for secant is secant tangent. And so that is my integration rule. So you'll see if we compare these to the derivative rules, these are just the opposite. They're just flipped. All right. So let's talk about u substitution here. And we'll do a few examples. Okay. We're going to let u be the inside function. Then we find the derivative of u and solve. Oh, how do I want to reword that? Sorry. Hold on. I'll come back to that. Hold on a second. Substitute these expressions for the integrand function. And its derivative. Integrate. And make sure to replace u at the end. In this spot here, I think I'm going to have you write, and I forget what I had originally, but you want to find the derivative of u, whatever that is, and solve for, or maybe I should say isolate what you have in your integrand. Oh my goodness, sorry, you can't see any of that. I apologize. Okay, isolate what you have in your integrand. Integrand being this part here, okay? Alright, you might need to pause the video to write that down. I'm going to go on to example 2 here. So this is where you get some examples where we're going to have to use substitution because it's not the straight power rule, okay? So we'll say 4v plus 9 squared dv. Now, this is not one we can split up because you're squaring. We also can't just use the straight power rule here because we don't have x to a power. We just have a u to a power, like an inside function, okay? So we're going to let u be your inside function, which is 4v plus 9. And then we're going to find du. Now again, we're doing some substitution here. So the function actually integrate isn't going to look like this at all. We're going to start plugging stuff in after we find good substitutions. My du then is the derivative of this, which is going to be 4. And since I took the derivative of a v, I'm going to include v. You'll notice when I go to substitute, I can put u in for this. All right, and we're actually going to do that here. Okay, so instead of 4 plus 9, I'm going to perform the substitution. And then I just have dv. Okay, so I need to replace dv. And so if that's what I need to replace in the integrand, then I'm going to move the 4 over by dividing. Or you can look at it as, maybe better to look at it as 1/4 du. Okay, so we're going to divide and get good substitution. So instead of dv, I'm going to replace dv with this expression. Now, the du is fine. I can just leave it there. But the 1/4, that constant, I'm going to pull out in front. Okay, so you should be able to replace every part of what you see using u substitution. And then you'll notice this becomes a very nice problem here because I can just use the power rule for integration. Okay, so we're going to add 1 to the exponent, divide. And that's why we do use substitution, because a lot of times the function that we end up with to integrate is much simpler. Okay. So I'm going to add 1 to the exponent and divide. Add 1 to the exponent gets me 3. Dividing by 3 gets me 1/12 u cubed plus c. Now, this is not my final step because I do have to replace what u is. So I'm going to perform my substitution again and replace u, my final answer. It's 1/12 4v plus 9 cubed plus c. Now, if you're not sure you did it right, you can always take the derivative of this, and you should get what you started with, which you would here. Okay. We'll do one more here together, I think. Let's go with this one. Y equals integral of tan to the 7th of x times secant squared of x dx. Now, we're going to use the substitution here. You have to decide what the inside function is. I'll give you a little hint. If there's a power greater than 2, that's usually your inside function, because if you notice, hopefully that rings a bell, that the derivative of tangent is secant squared. So you don't want to split that up too much. I'm going to let u equal tangent of x. Du, or the derivative of that then, would be secant squared x dx, which is helpful here, because then I don't have to perform any weird substitutions, because that gets replaced by du, that gets replaced by u. So I'm going to rewrite, and I get u to the 7th du, and then it's a very straight power rule here, where you add 1 to the exponent and divide. And so you get 1/8 u to the 8th plus c, and then replace the u. And again, if you're not sure you did it right, take the derivative again if you get what you started with, which you would, because you have to do the chain rule, and then you would get that. Okay, so we'll do example 4, 5, and then get into some of the particular solution next few days. That at least gets you a glimpse at what u substitution is and how we're going to start using it with simpler functions.